Now we will take a look at the most important reaction in the chapter of carboxylic acid derivative. It's called nucleophilic acyl substitution. It's a substitution reaction that takes place on the acyl group, but it does not take the same mechanism as SN1 or SN2 that we have talked about before. So basically, if we start with an X attached to the acyl group, a nucleophile Y- could replace this X to make a new compound. And the nucleophilic acyl substitution is used for the interconversion of acid derivatives. Okay, we can convert one acid derivative to the other through this reaction. And all the carboxylic acid derivatives can be hydrolyzed to carboxylic acid through this acyl substitution. The general mechanism for nucleophilic acyl substitution involves two steps. The first step is called nucleophilic addition to carbonyl carbon. This is the same step for the reaction of aldehydes and ketones. When you have a nucleophile, the nucleophile will attack on the carbonyl carbon, breaking the CO double bond to form the tetrahedron intermediate. Okay, that's the same step, nucleophilic addition to carbonyl carbon. The second step in the nucleophilic acyl substitution is elimination. This is different from the reaction involving aldehydes and ketones. In the elimination, the CO double bond reforms, the carbonyl reforms, and a leaving group leaves. Alright, so you should be very familiar with nucleophilic acyl substitution already. We have talked about three reactions that go through this mechanism. They are Fischer esterification, hydrolysis of ester, which is the reverse of Fischer esterification, and the Grignard reaction with esters. So I would recommend you to review these reactions now before you continue. So now I'm going to use hydrolysis of acyl chloride to illustrate the mechanism of nucleophilic acyl substitution one more time. Hydrolysis of acyl chloride will give carboxylic acid. So when acyl chloride react with water, carboxylic acid is formed and HCl is the byproduct. The first step of the mechanism is the nucleophilic addition of nucleophile, water in this case, attacking on the carbonyl carbon, breaking the CO double bond to form the tetrahedron intermediate. So water attacking on the carbonyl carbon break the CO double bond. Now we have the tetrahedron intermediate. And after proton transfer, we get the neutral tetrahedron intermediate. The second step, elimination, or the dissociation of the tetrahedron intermediate. And this is actually a dihydrohalogenation reaction. So water could serve as the base, and it will remove the hydrogen on the oxygen, and the CO double bond forms. The chloride leaves as the leaving group. So this mechanism is pretty much the same as the base catalyzed the dehydrohalogenation mechanism. But right now it takes place between an oxygen and a carbon. So this step gives carboxylic acid as the final product, and hydronium ion and chloride. The overall result, the OH replaces the Cl on the acyl group. Now we need to take a look at the tetrahedron intermediate one more time. When the carbonyl reforms, when the CO double bond reforms, we are going to break a bond on that carbon. So we have three potential leaving groups here: the R minus, the OH minus, and the Cl minus. Okay. Again, when we form the double bond on the carbon, we have to break a bond. So these are the three groups that can leave. And this reaction gives carboxylic acid as the final product, which means the chloride has to be the leaving group. And the chloride is favored as a leaving group. The loss of chloride is much faster compared to the bond breaking for the other two groups. This is because chloride is less basic and it's a better leaving group. So if you compare the basicity of the three groups, R minus is very basic. So it's the most difficult group to break. Hydroxide is relatively basic, but the chloride it's neutral. Okay, it's less basic, so it's a better leaving group compared to the other two. That's why chloride will be the leaving group here, and the final product will be a carboxylic acid. Now I just want to say a few words regarding this nucleophilic acyl substitution compared to the nucleophilic substitution that we have talked about before. The acyl chloride reacts faster than an alkyl chloride in nucleophilic substitution. Actually, acyl chloride reacts 1,000 times faster. There are two reasons for this. First one is the steric reason. In acyl chloride, we have carbonyl, so the carbon is sp2 hybridized, which means it has only three groups attached to it. It's less hindered compared to an sp3 carbon in alkyl chloride. It has four groups. It's more crowded. Okay, for steric reason, acyl chloride is favored. And secondly, the intermediate in acyl chloride acyl substitution is tetrahedron. And the tetrahedron intermediate has stable arrangement of bonds. It has lower energy, so it forms faster. This is compared to the reaction of alkyl chloride. If it goes by SN2 mechanism, then we have the penta-coordinated transition state. If it's SN1 mechanism, we have the carbocation intermediate. For both cases, those are not stable intermediate or transition state. Okay, penta-coordinate, there are 5 bonds around the carbon, not very stable. And the carbocation, there are only 3 bonds, so not very stable either compared to tetrahedron intermediate. Carbon is stable in the tetrahedron form, right? So because of these two reasons, the acyl chloride will react faster than alkyl chloride in nucleophilic substitution. Alright, now let's go over it one more time regarding the reactivity of carboxylic acid derivatives toward nucleophilic acyl substitution. We have explained this before. For acyl chloride, acid anhydride, esters, and amide, if we take ester as our standard, suppose the reaction rate for ester is 1, then the acid anhydride reaction rate will be 10 to the power of 7th. So acid anhydride will react 10 to the power of 7th faster than esters. For acyl chloride, 10 to the power of 11th. It reacts much faster than the compounds listed below. And for amide, 10 to the power of -2. That's the relative reaction rate. Amide is the least reactive. Okay? So it is in this order that the compound on the top will be most reactive, least stabilized, while the compounds at the bottom will be least reactive and the most stabilized. And to put it in another words, a more reactive derivative could be used to prepare a less reactive one, but not the reverse. That means we can use a compound on the top to make a compound at the bottom. So, for example, for esters can be made from acyl chloride or acid anhydride, but esters cannot be made from amide. Does that make sense? Alright, now, based on this explanation, I want you to take a look at these two tetrahedron intermediate. And I want you to tell me what reaction will give this tetrahedron intermediate. Or, in another word, what product will this tetrahedron intermediate break down to? Okay, so I want you to think about it, and we will check the answer in class. I just want to give you some hints. If you focus on the first structure on the left, that's the tetrahedron intermediate. And in the product, we are going to form the carbonyl. The carbonyl will be from the OH group on the top. So when the electrons on that O comes back to reform the CO double bond, one group on the carbon has to leave. Now the question is, will CH3 leave, or OCH3 leave, or NHCH3 leave? Okay, so one of them will leave and the rest will stay, and that will be your product. Alright, so think about this and try to get your products from these two tetrahedron intermediates.